Okay, guys, so in this video, I want to introduce measures of relative standing. Basically, why do we need measures of relative standing? When we want to compare two values from absolutely different distributions, and maybe distributions that even have different measuring units. How to do that? Measures of relative standing will help us in that avenue. So for example, I just wanted to give you an example. I'm making it up on the fly. So let's say you are a biologist studying whales, and you come up and you're observing a whale that weighs, I don't know, 3 tons. And then also, is it a big whale or is it a small whale? And then uh, you have a guppy fish, which is, let's say, 1 inch long. Is it a big guppy fish or is it a small guppy fish for, you know, the guppy size? So, and how do we compare like that 3 ton whale to this guppy fish that's 1 inch long? Or like, which one of them is bigger in their population? So basically, measures of relative standing help us to compare apples and pears. Let's explore this topic a little bit more so you got a feel of why it is important. I want to ask you, let's say I have a friend and who is taking biology and physics this semester, and she told me that she got a score of 40 on her biology exam and a score of 90 on her physics exam. So which score do you think is better? And I want you to pause here and to think about this question a little bit. Keep in mind that these are not percentages. These are raw scores, okay? What do you think is better? Also, if you said that you cannot compare those two scores, which information would you need to answer the question be more informed about the situation? So pause here and think about answers to those questions. All right, so a lot of students here say, well, we want to know what the maximum number of points was, just in case if these are not percentages and just raw points, which, yeah, that's what they are. And some say after a while, they say, okay, we also want to know the average. Um, if the exam, let's say exam is graded based on the curve, what's the average score? Did I do better than the average or not? Okay, so here I give you some the average scores for each exam, and that is helping a little bit. Like you could tell that she did better better than the average in both of the classes, but is it a complete information? In order, okay, so yeah, if one was below the average and one was above the average, then that's clear. The one above the average would be better score. But now for these two, both of them are above the average. So in which class did she actually get a better grade? Okay, so we need a little bit more information again. So what kind of information would you want to know? Tell me right now. Which information do you need to know in order to answer that question? So what do you think? I'll tell you which one I would like to know. I would like to know the standard deviation. And so the standard deviation for the first exam is 5, and the standard deviation for the next exam is 7. And here's why I want to know that information. So here, let's pretend these are our distributions. Let's pretend that they're normal, even though usually they're not. But so for our sake, we say they're normal. So I have a mean of 30 and the standard deviation of 5. So if I go one standard deviation above the mean, I land at 35. And then one more standard deviation above, I get 40. Okay, and this is the score of our friend right here, 40. So she is 2 standard deviations above the mean, which means that here's the 50% of all students, and this percentage is 47.5%. So she is actually in the 97.5 percentile. Okay, so only 2.5% of students are above her. Only 2.5. Now for the second score, we have the mean is 80 and the standard deviation is 7. So one step above is 87. One more step above is going to be 94, and that's already bigger than the score that our friend got. So she's somewhere here. So she's below 2 standard deviations. So see, there is more than 2.5% of students above her. Okay, so even though she scored pretty good, not saying anything, but this score is still higher relative to how the rest of the class did. Okay, so now the question is, we're not always going to land exactly on 1 standard deviation above or 2 standard deviations below, or vice versa. Sometimes we're going to land in the middle like that. So the question is, how do we figure out how to compare those scores? Yeah, what if one was slightly above 1 standard deviation and the other one is slightly below? How would we figure it out? Or maybe they're in the same vicinity, both between 1 and 2 standard deviations away. How do we compare them? Well, there is a formula that helps us to basically standardize, find the exact distances from the mean in terms of standard deviation. So how would you do, and it's called a z-score. Okay, so how would you figure out that z-score here, for example? So you find the difference, 40 minus 30, and so that will give you a distance of 10, and then you're gonna divide in the step length, or the standard deviation, your unit. Okay, so divide by 5, and that's going to be 2. So that's 2 standard deviations above the mean. Okay, and for this one, you would do 90 minus 80 divided, so the distance between the two divided by the step length, or the unit, your standard deviation, 7. And you put that into a calculator, and we get 1.42857 about. There's more decimals, but I'm gonna round it anyway. I'm gonna round it to 1.43 because the next value is 8. It's 5 or more. You round up. All right, so the formula that we use, it's just it's called a z-score. So this is Z1 and this is Z2. All right, so let's write down the formula. So z-score formula is your x value minus the mean of the sample divided by the standard deviation of the sample. So that's a z-score for a sample, and the z-score of the population is similar, just different symbols. X minus the mean over sigma. So it's the same formula, just different notation. So that's a little bit, let's talk a little bit more about z-scores. The z-score tells you exactly where your data point is located in relation to the center. So if your data value is above the mean or the average, then your z-scores are going to be positive. By the way, these right here in red, those are z-scores. But so far we were talking about the exact steps, like 1 standard deviation, 2 standard deviation, 3 standard deviation. With a formula for the z-score, now we will be able to calculate the number of standard deviations in between 1 and 2, or 0 and 1, or -2 and -1. So z-scores that are positive are go to the right of the mean, so they're increasing that way. They're positive, and if the data values are have a negative z-score, what that means is that they are below the mean. So that's a very important observation. Okay, now another thing that I wanted to mention here is that your mean value has a z-score of 0, because this is the center. This is where we start counting the distance from the mean. So the mean value is 0. And I want you to notice that we kind of have two different scales going on here. So these are your x values, your actual data values. And these in red, they're z-scores. For example, if you remember our examples about IQ scores, the average IQ score was 100. So this mu here would be 100, and it would have a z-score of 0 because it's right in the center. And the z-score, again, it measures the distance from the center. So if you go one standard deviation above, you would hit 115. 2 standard deviations above, 130. In a similar way, if you go below the average, so 100 minus 15 is going to be 85, 70. So these are now they're symbols, because they're this picture is very general, but when you're working with specific distributions, those are going to be numbers, and those numbers will be associated with the z-scores. And in the future, we're going to be converting between these back and forth. So it's one of the important features that I wanted to point out.